Yeah, great pleasure to introduce to the stage now Doug Wiens. We're going to move on to seismology now and how we can image mantle melting. That's on straight away.
Well, I'd like to thank Rich for organizing this wonderful conference and for inviting me. And I'm pleased to be here. I'm really looking forward to getting some feedback on some of these ideas here. I think the last time I gave a talk in Cambridge, it was the day that all the planes hit the World Trade Center. So I hope that things go a little better, a little better today. So I guess we're starting out with some observations about melt, and so I've been working on imaging island arc systems in the Western Pacific, and I think there's some real advantages to imaging these systems with seismology. For one thing, we have lots of earthquakes immediately beneath the sort of relevant magmatic systems, so we have sort of an ideal imaging geometry from a seismology standpoint. Another really interesting aspect of these systems is we have two different melting systems, and probably two different, maybe the two most important melting systems in the world, sort of in the same area and interacting. And so we have both the flux melting from the slab, and we have decompression melting largely in the backarc spreading center. And so we can image them both, and we can also image the interaction between these two melting systems. Furthermore, by looking at spreading centers, backarc spreading centers at different distances from the arc, we can actually look at different amounts of water in the melting system, because we know from fluid inclusion studies, like this study by Katie Kelly, where when we're closer to the arc and to the trench, we have much higher water contents in the melt source material. And so because spreading centers at different distances from the backarc are sampling different areas of the mantle, we can infer then that the closer we are to the slab, the higher the water content in the melt source, or in the mantle source material, and thus we can study the influence of water on the melting process. And of course, there's a lot of interaction then with geochemistry and with petrology that are very interested in these kind of interactions. So, and we've been for quite a number of years now imaging these systems using ocean bottom seismographs. I mean, the one disadvantage of the Western Pacific island arcs is that most of the area is underneath water, and so it presents more of a technological problem in terms of actually imaging these systems with seismology, so we have to use ocean bottom seismographs. And I'll mostly be talking about a couple of large-scale ocean bottom seismograph experiments that we've carried out. The first one was in Mariana Arc, which was a joint US-Japan program, and then the second one was a study that was funded by the US Ridge 2000 program in Tonga. Just to be really quick about it, these use ocean bottom seismographs from the three US equipment or pool organizations, which are slightly different, but they're all involve broadband sensors that can remain on the ocean bottom for up to a year, or now I think up to 18 months. And just to kind of really quickly go through what we're looking at, and this is kind of a relatively simple model of arc melting, and I think in this meeting you're probably talking about more complicated models, but the basic idea behind arc melting is that as the slab subducts, that dehydration reactions in hydrous minerals in the subducting slab result in a lot of water being given off at depths between maybe 75 and 150 kilometers, and that water moves by porous flow, and in this model forms melt in the hot part of the mantle wedge, and then the melt moves by porous flow upward to the arc. And then, of course, these systems we'll be talking about also have backarc spreading centers, which, for the most part, we believe have a spreading system which is very similar to a mid-ocean ridge, where we have decompression melting, perhaps starting with very small degree of melts, water-assisted melting at considerable depths, then the main region of melting, which would be shallower than about 60 kilometers to maybe like 15 kilometers depth, and then the melt would move upward by porous flow or by channels. Okay, so as an outline to this talk, I'm going to talk just a little bit about how we can understand mantle melting using seismic systems, and that involves a little bit I'll mention a little bit of experimental work, and then I'll talk a bit about sort of empirical observational evidence for melt from our seismic data. In other words, how it appears that we're imaging melt in the mantle from seismic results. I'll talk a little bit about how much melt is in the mantle, and then go back to the arc and backarc melting systems and talk about the Tonga, what we can learn from the Tonga-Lao system. So first of all, the main seismic observables that we can use to try to infer the presence of melt, we can measure P velocity, S velocity, P attenuation, S attenuation, and then anisotropy. And it's possible, of course, to infer the presence of melt perhaps from anisotropy if you have oriented melt bands. That's something I won't talk about very much, but I think Mike Kendall may talk about that in his talk later on. So I'm going to focus on mostly these first four things. Of course, VP and VS are functions of the elastic moduli, which might seem rather straightforward, but we also, because of anelasticity, we have a frequency dependence of the elastic moduli. And so, if we hit an Earth material with a stress unit step function, then we get a response that looks something like this, where we have an initial instantaneous elastic response, and then we have a creep function, okay, which would be an anelastic response. And so, we can visualize it maybe using something like this, where we have a spring representing the elastic response, and then we have a spring dashpot system representing the anelastic response. And so basically the result of that is that we have sort of elastic moduli that vary with frequency, okay? And so and the amount that they vary with frequency is essentially proportional to the attenuation. The attenuation is related to this anelastic response. And so that means that the elastic moduli that we see will depend on the frequency at which we're, essentially forcing the system with. If we're forcing it at a very extremely high frequency, then we're sensitive only to the purely elastic moduli. But if we're forcing it with a lower frequency, then we're sensitive to the relaxed moduli. And so that part of the system is relatively hard to characterize. So another aspect of this is that the anelasticity is usually assumed to result only from the relaxation of the shear modulus. And if that is the case, then and all this anelasticity is associated with the shear modulus, then we would predict that QP would be 2.4 times QS, or in other words, the shear wave attenuation would be much greater than the P wave attenuation. And so we can actually test this idea in the real world. Okay, so I'm very briefly talking about experiments. So the result of the anelasticity is that we can't study the effect of melt on seismic properties using ultrasonic experiments or something like that. We have to actually do the experiments at seismic frequencies. And so that makes these experiments relatively hard to carry out. Ian Jackson's group is one of the groups that's been doing this kind of research, and Takei-san's group, University of Tokyo, is another one of the groups that's been doing these kind of experiments. And this is at least one way those experiments are done, essentially by using a torsional forcing of the sample. And then you can do the torsional forcing at seismic frequency and therefore measure how the modulus changes as a function of frequency or temperature and other factors. As a result of this, we have some understanding then of how temperature affects seismic velocity and attenuation. This is the result of some results from Ian Jackson's group. And we think that the results are largely independent of the anelasticity at temperatures below about 900 degrees C. But as you get closer and closer to the solidus, then the anelastic effects become more and more important. There is still a lot of controversy about exactly how to parameterize the temperature effects, but they all the results are somewhat similar in their predictions, and they all show something like this, where the S velocity decreases fairly rapidly with temperature above about 1,000 degrees C. But it's hard with temperature effects alone with mantle materials to get velocities that are much below 4.0 kilometers per second for shear velocity. And then there's alternative ways of looking at this, such as Priestley and Mackenzie, where you're taking a more empirical approach and looking at the seismic velocities that we observe, and where we know something about the temperatures in the Earth, and using that to calibrate. And that comes out with results that are not terribly different from these kind of results. The experiments with melt, though, are quite difficult to do, and I would say that they're still in progress. I'm hoping to hear more about the most recent results from Takei-san's talk later this week. But there's some indication that even a small amount of melt can produce a very large effect in seismic attenuation. And that comes from these experiments by Fowle and Jackson and others in 2004, and experiments by Christine McCarthy and Takei in 2011. And they both show that a relatively small amount of melt on the order of 1% or even less than 1% can produce a large increase in the amount of attenuation. So suggesting that even small melt porosity can have a relatively large seismic effect. One other thing we have to worry about is the effect of water, and Shun Kurado's done quite a bit of work on this, although there's no experiments that sort of well characterize this system either. The work that Shun's done basically extrapolates from the effect of water in olivine on the rheology of olivine, and he has this figure here where he's showing how the change in the amount of water in olivine will cause perturbations to the prem attenuation for the asthenosphere, and So one of the things here is that the amount of water that you can absorb as an anhydrous, as water within the normally anhydrous peridotite in the upper mantle is relatively limited, and becomes greater as you go deeper in the mantle. But that limited amount of water can really have a relatively limited effect on attenuation, can reduce it from about 80 to 60 and cause maybe a 2% decrease in seismic velocity. So that suggests that water would not have a predominant effect on what we're observing near volcanic arcs, where we have large water content in the mantle. Okay, so now to go to some empirical or observational evidence on what we can see with seismology. And this is an example of our imaging across a volcanic arc and backarc spreading center system. This is from the Mariana Arc. This is P-wave tomography, and going down to 150 kilometers in this image here, we see the high velocity slab. Beneath the volcanic arc, we see these very low seismic velocities here that go actually, this is a little bit offset. I must have moved it. But the highest anomaly here is at 60 kilometers deep, and the largest anomaly in the backarc spreading center here is about 25 kilometers deep. And the correspondence of these very low seismic velocities beneath the volcanic systems here suggests that we're actually imaging the melting system beneath the arc and beneath the backarc spreading center. And one of the interesting things here is we can compare these anomalies with estimates from thermobarometry, from petrology, as to how deep and at what temperature these magmas are coming from. And so Katie Kelly's paper in 2010 suggests that the arc magmas, their last equilibration depths are between 34 and 87 kilometers deep. And in fact, beneath this volcanic system, the last equilibrium depth is between 50 and 60 kilometers. So right at the top of this large velocity anomaly. And beneath the backarc spreading center, they're much shallower. The last equilibration depths are 21 to 34 kilometers deep, which agrees very well with the 25 kilometer deep depth of the maximum anomaly that we see from our tomography. Yes?
What exactly you mean by equilibration depth? Is a time of residence?
Yeah, I mean, I'm not a petrologist or a geochemist, so what I believe, I think that has to do with the last time that the major element composition of the magma is in equilibrium with the matrix. Okay.
Where you go from slow migration to fast migration.
You might interpret it that way. That would be something that, I don't know, the modelers may want to chime in on if they actually explore how the petrology and geochemistry reacts between the melt and the matrix. But that's kind of how I understand it, is that would be that you probably have equilibration where the melt and the matrix is relatively slow moving yet at that point. Maybe you don't have channels or something. So anyhow, there's really good correspondence then between the depths of these anomalies that we're measuring here and what petrologists are inferring about the melts that are coming out of these systems. And in this case, we have shallower systems for decompression melting beneath the backarc spreading center, somewhat deeper systems beneath the volcanic arc. And there's another very interesting recent paper by Terry Plank and Don Forsyth where they look at this for the western U.S. And this is mantle tomography from Don's group at 70 kilometers depth. And you can see that you get very low shear velocities of about 4.0 or 3.9 only beneath these areas that have recent volcanics, which are these black dots. Okay, And so there's a correspondence then between the low seismic velocities at 70 kilometers deep and where we see recent volcanism within the last million years in the western U.S. And so they did a joint study then looking at the thermobarometry of those magmas and the temperature structure as inferred from seismology. And so that's where this figure comes from. So this black line here is the geotherm that was inverted from the seismic data using relationships between seismic velocity and temperature. And in basically this bullseye there, the two contours, is the uncertainty region on the melt equilibration depth and temperature from petrology. So you can see that basically this magma was coming, or this melt was coming from 60 kilometers deep and a temperature of about 1380 or something like that. So in general then, what we're seeing when we compare petrology and the seismic results is that the melt equilibration depth is generally at or immediately above the lowest velocities. And in this diagram here, this dotted blue line is the seismic velocity profile. So the lowest velocity point here is about 70 to 75 kilometers deep, and the melt equilibration point is about 60 to 65 kilometers deep. And so it looks like the melt is equilibrating then at the very top of the region that has the adiabatic gradient before you get into the conductive gradient of the overlying plate. But I guess the point that I'm trying to make here is that it looks like we can do a very, quite good job with these low seismic velocities of inferring the place in the mantle where the melt is being produced. Okay. And just further evidence, I guess. Oops. Let's see here. Further evidence for this is just if we try to fit our seismic images using all the other known factors that can influence seismic velocity, like temperature and water content, we just totally fail to match the slowest seismic velocities. So this is one of our images that we'll talk about later on from the Lau Basin, is showing seismic velocities getting very low, down to about 3.7 or so kilometers per second here beneath the backarc spreading center. And then this is estimated seismic velocities that we would expect using a geodynamic model that has a subducting slab in a backarc spreading center, and also has water contents that are elevated near the subducting slab, and taking into account the effect of water using the relationships from Corrado. And you can see that although we can, to some extent, match some of the structures that we see, such as the slab and the overall mantle structure here, basically we totally are unable to match, the velocities from this lowest, from the lowest seismic velocity region, suggesting that there's additional factors there which we would infer to be the presence of melt. And the lower figures here show the same general effects for P-wave attenuation. So this is our attenuation model for the Lau and Tonga region. Extremely high attenuation here beneath the backarc spreading center. And then this is what we would predict for the attenuation structure just on the basis of temperature, where the temperature is inferred from metrology of the backarc spreading center, and elevated water content. So basically, we really require melt in order to even come close to matching the seismic velocities that we see. One other thing that suggests that we're really imaging melt is that we see bulk attenuation. So we usually assume that seismic attenuation is associated with the relaxation of the shear modulus. All the experiments that have been done on seismic attenuation are looking at shear attenuation, in other words, the relaxation of the shear modulus. But normal modes show that there is little bulk attenuation in the whole Earth, except for a small amount of bulk attenuation in the uppermost mantle, or the asthenosphere. And so there is the possibility that bulk attenuation is a factor. And if we only have shear attenuation, we predict QP to QS ratio of 2.4. And then this is the attenuation, the bulk attenuation that we observe in the Tonga-Lao region. And so in the far backarc, like away from the backarc spreading center, we observe very low bulk attenuation. We observe QP-QS ratios of about 2. And I'm sorry I don't have the bar up here, but this blue color here is about 2 for QP-QS. But near the backarc spreading center, we observe a QP-QS ratio of about 1. And that corresponds to an almost equal contribution of bulk attenuation to shear attenuation, suggesting that bulk attenuation is actually a major factor in the attenuation structure of the system. But we only observe a significant bulk attenuation in the area of the backarc spreading center and the volcanic arc. And I should say that we have relatively low resolution. It's a difficult measurement to make, we've made it before, but we've always kind of discounted it as being something that's not very well constrained. But we think now that we can definitely show that there is bulk attenuation, and it is concentrated in the area of the backarc spreading center. And if we have bulk attenuation, that implies a relaxation process probably resulting from melt. Such as melt flow between the pores resulting from pressure gradients. Or another possibility is phase changes introduced by wave passage. So if the passage of seismic waves introduces any slight perturbation in the melting properties of the two phases, then that would also contribute to absorption of energy or bulk attenuation. So that's another indication, the fact that the bulk attenuation is concentrated in the area where we expect melt. So, some of our summary here would be strongest anomalies are concentrated directly beneath volcanic systems. The anomalies are too large to result from temperature alone, and the strongest anomalies correspond well with the depths that we expect melting. The strongest anomalies correspond well with the equilibration depths from thermobarometry for the top of the low velocity regions. One question here that I'm going to talk a little bit about is how much melt is present. Because one of the things that is kind of concerning to me is I read sometimes in literature that the upper mantle contains, 2 or 3% melt porosity. There's 2 or 3% melt by volume in the upper mantle, and it's based, people will quote something like, well, that's based on the results of the melt experiment, or that's based on the results of the seismic experiment, or something like that. Well, those seismic experiments have just recorded like seismic velocities, okay? And so the actual connection of seismic velocities to the melt porosity in the mantle is actually pretty tenuous. And I think Rich mentioned some of this in his introduction, but experimental evidence from what melt geometries actually look like, from like Wen Lu Zhu's group, and this is one of these images, suggests melt permeability should be very high, even for a very small melt porosity. And that suggests that melt should be efficiently extracted from the upper mantle. There's also geochemical evidence for a relatively rapid movement of melt through the mantle. So together this indicates that we may not expect to see very high melt porosity in the mantle. So is the seismic data actually indicating that we have a large melt porosity in the mantle? And this is kind of an interesting case here from the Mariana Arc, where we have both p-velocity tomography, and I already showed sort of the upper part of this image. And then we also have a resistivity image from ocean bottom MT survey. And one of the interesting things we see here is that for the arc, we do see a large seismic velocity anomaly here at about 50 to 60 kilometers deep. And we do see a low resistivity area coming up to about 50 or 60 kilometers deep, suggesting there's some high conductivity fluids or melt in that area. But when we compare the backarc spreading center, we see significant seismic anomaly there, but the uppermost mantle in the resistivity image is highly resistive. And so it looks like the resistivity image here really fails to sense any melt beneath the backarc spreading center. So, how can we reconcile these two images where in seismology we apparently see a substantial signature of melt in the backarc, and with resistivity we fail to see that?
Is this the active spreading center?
Yes, it's the active Mariana backarc spreading center. So it's about, I think, 18 north. So, and the seismic line and the resistivity line are approximately the same location, say within 100 kilometers. So, it's hard to really explain that difference. Matsuno et al. Carried out some experiments to say how much melt could they hide in their resistivity image. And so basically they introduced several different melt geometries, such as a rectangular geometry, which was continuous along strike, a triangular geometry, which was continuous along strike, and then a pyramidal geometry, which was not continuous along strike. In other words, you had sort of a single pyramid of melt sort of beneath the study area. And the study area was close to a high topographic point on the backarc spreading center. So even though we assumed that maybe slow spreading centers like the Mariana spreading center might be discontinuous along strike, you would expect that this area where they did the survey would be one that would have melt present. And so they took this and then they generated synthetic data and they reinverted the model. And then they looked at then the difference between the reinverted model and what they got from their inversion of the actual data. And so for the rectangular case, there's really very large differences between the reinverted data, synthetic data, and then the reinverted, or in the inverted actual data. So they could pretty much rule out this case. For the other two cases, they could actually hide the melt, essentially. In the model, if the melt was very low, had a very low porosity. Okay, so that they could get for the pyramidal case, they could hide the melt if it was 0.1 to 1% connected melt porosity, within this region. And for the triangular case, they could essentially hide the melt if it was smaller, sort of on the order of 0.1% melt. In that sense, I think we can make the story consistent if the seismic velocities are very sensitive to actually very small quantities of melt, on the order of less than 1%. I also, a few years ago, made a calculation using the Jackson et al. Experimental relations, where they had determined an attenuation relationship for a sample containing melt. Now, Ian Jackson said there's several difficulties now with that experiment, but just taking what they published, we can make a contour plot of the expected shear attenuation for different temperatures and different melt porosities. Here's between 0 and 1.5 percent melt porosity. We observe a shear Q of about 25 for the Lau Basin and 40 for Mariana, and those are shown here as the white line for Lau and the red line for Mariana. And we also know the temperatures from petrology, about 1450 for Lau and 1350 for Mariana. And so that allows us to see where we match the attenuation matches that would be predicted by the Jackson et al. Experimental results, and it's about 0.1% melt porosity. At least using those experimental results, we can match the high attenuation that we see in these areas with only a very small amount of melt porosity. And so the question, I guess, then is large melt porosity possible in the mantle, at least over a large area? I noticed in Richard's plot, of the models of mid-ocean ridges, he got 2 or 3% melt porosity, but only in a very thin layer, sort of at the very top of the melting region, where the melt seemed to pool, or something like that. And it's kind of interesting. So this was a really nice MT image or resistivity image from an MT experiment along the East Pacific Rise. But one of the interesting things about it is that the very, very low resistivity that they found beneath the ridge, they said corresponded to greater than 10% melt porosity. So I don't think they pushed that very far, but there's certainly some inconsistency here between the amount of melt that would be inferred from this MT image and what I think most of the people who model these systems in this room would expect is there. And so I don't know enough about resistivity to know how well constrained these relationships are. I know over the years there's been this kind of discrepancy, I think, between several groups in how to interpret resistivity data. But I think one has to be wary of over-interpreting, I think, images like that in terms of the melt porosity. And I think that the amount of melt porosity in the mantle is still very uncertain from seismic and resistivity observations. I think it's probably quite consistent with very, very small amount of melt porosity in most cases. So now, just to go on for the last part of my talk, I'm going to talk specifically about the Lau Basin, which is a very interesting area because the area that we've looked at here has a volcanic arc, and in a backarc spreading center that begins in the north, very far away from the arc, several hundred kilometers, and it begins in this area. It erupts pretty much normal morb. Okay, going south along this arc, then the backarc spreading center erupts larger and larger amounts of fluid mobile elements within the basalts, and eventually ends up erupting andesite at the very southern end of the backarc spreading center. And there's sort of a geochemical discontinuity here where I have this dotted line, and you can see that on a couple of these plots here. And in particular, south of that area, we see much, much larger effect of fluid mobile elements coming off the slab. So it's easy to understand why you might have a gradual increase going south along this arc in fluid mobile elements, but it's hard to understand why there would be sort of a discontinuous increase in fluid mobile elements at this position. And so some of the results of our ocean bottom seismograph experiment, this is an image from noise correlation, which is sensitive to the uppermost mantle structure. And this is at a depth of about 25 kilometers. And it's compared here with the geochemical discontinuity results, and then also axial depth on this side. What you see here is in the northern part of the eastern Laos spreading center here, the very low velocities are, and presumably representing the melting region, are offset towards the west, okay, of the arc. So like there, at 20 south, the main anomalies are all to the west of the spreading center. But as you reach this geochemical discontinuities here, the main anomaly jumps over to the eastern side of the eastern Laos spreading center and is now centered sort of halfway in between the volcanic arc and the backarc spreading center. So it looks like the cause of this geochemical discontinuity here is the fact that at this region you start to essentially merge into almost one melt production region for the backarc spreading center and in the volcanic arc. And some larger scale imaging then by my student Sean Wei are in this figure here. And what we see in the larger scale imaging from surface waves is that we have extremely large, extremely low velocities throughout much of the northern and central Lao Basin. We also see that we have a very large velocity anomaly here at about 50 kilometers depth that is not well separated between the volcanic arc and the backarc spreading center. There's some evidence of a little bit of lithosphere there in between, but for the most part, this velocity anomaly is pretty continuous here, and it extends to the west. So our understanding of this is that we would have a subducting slab here that would drive mantle flow in sort of a corner flow pattern, and then the rising mantle flow to the west of the spreading center here would bring mantle material up, and you'd have decompression melting sort of centered a little bit to the west of the arc. And we see a sort of similar structure here on the attenuation structure. Once again, extremely large attenuation anomaly beneath the backarc spreading center, and it extends deeper and towards the west. Then in trying to understand this, once again, this geochemical discontinuity here at about 21 south, if we look at three profiles, A and B and C, in profiles A and B, which are located to the north of the geochemical discontinuity, we do see this large tail going diagonally and deeper to the west, and that we infer to be rising mantle flow moving into decompression melting to the west of the spreading center. And essentially, some of the melt is being fed in from the west in these areas. But when we get to the southern part of the Lao Basin, south of this geochemical discontinuity, there's no longer any connection to the west, and the velocity anomaly is much smaller and is sort of centered right above the slab. So in this area, we would infer that the backarc spreading center is actually just sort of essentially sampling the mantle in the vicinity of the slab and no longer being fed by this upwelling system from the west. And so that transition apparently happens, both at shallow uppermost mantle depth and at this larger scale at about this point where we see the geochemical discontinuity. And one other thing that we're really sort of fascinated about the system here is that when we look at a north-south profile, So this is looking at a north-south profile D to D prime throughout this system. Here we see extremely large velocity anomalies to the north, even in areas that are not directly underneath a spreading center. And then along this profile, we have the eastern Laos spreading center, where we also see extremely large velocity anomalies. And then going southward, the velocity anomalies sort of peter out and become shallower and become smaller. And of course, the southern part is the part that has the large water input from the slab, and much larger amounts of water in fluid inclusion studies, and much larger amounts of water from slab mobile or from fluid mobile elements. And so we had sort of initially thought that we would see larger velocity anomalies where we have the large water input, just because we know that water might have an additional effect in terms of attenuation, and also because we know from petrology that we have larger extensive melting. In other words, a larger percentage of the mantle melts in the south, where we have the large water input. But instead, the seismic signature there seems to be much smaller. So initially, we thought it might be due to different temperatures. So we worked with Terry Planck to develop temperature estimates for the melting column in both of these areas. And the central Laos spreading center does have a somewhat hotter melting column, but that was not enough to explain the difference in the seismic velocity anomalies. And indeed, she gets a higher total extent of melting here to the south than in the north. So what we finally concluded was that we think that water is affecting the melt porosity. In other words, if our seismic velocity anomaly is roughly proportional, or at least sensitive to the amount of melt porosity in the mantle, that the areas that have a large water content may have a lower melt porosity. So if we assume that we have sort of very simple idea of Darcy's law melt flux, which is proportional to the grain size squared, the melt fraction to the n divided by the melt viscosity. We could imagine that water would reduce the melt viscosity extensively, and we may also, there are some studies that suggest that water increases the grain growth rate. So we could imagine that we could change this equation quite substantially by introducing water, and if that reduces the melt viscosity, increases the grain size, then for the same melt flux, we would require a much smaller melt porosity. So our interpretation of those results is that water essentially increases the efficiency of melt extraction, therefore requiring less porosity for the same melt flux. So in conclusion, then I won't read this whole conclusion slide. I think it would be better to just have some questions, but you can read it.
Questions, Doug? Ben?
What I'm wondering is whether the really low velocities are the result of melt, or of a high temperature process which we haven't yet understood, but without melt. And it seems to me that the only observation that you have which requires melt is the Q observations. That everything else, right, is perfectly explicable if the velocity drop is the result of some process which we haven't yet modelled, right, which happens very close to the melting temperature but doesn't require the presence of melt.
Well, I think if you're going to an argument on the asthenosphere in general, I think I may agree with you that many places the asthenosphere in general may be solely due to to essentially a solid without a melt, but a very high temperature. But in these cases where we're looking sort of localized regions beneath volcanic areas, first of all, we know that there's melt coming out. Okay, so there has to be melt being formed, and we have the additional evidence that, for example, our very low velocity anomalies correspond very well to the depths, from thermobarometry that the melt is coming from, and then it's very difficult to get such low seismic velocities without melt. So, I mean, I think if you take like...
I don't think we know that.
Well, I mean, there is some uncertainty in those relationships.
I think we know that.
Well, okay, but I mean, I guess I would then go back to the other two evidences that we see the melt coming out, and we know the melt.
The question that the melt is being produced in these.
Right. Well, but then the melt is also coming from sort of the exact depths where we're seeing these seismic velocities.
Closest to the melting temperature, obviously.
Yeah. So I mean, I think
distinguishing between the two.
I mean, I think what is a bit difficult to do, I think, is to exactly delineate. If you go to say some image, like say this one, to exactly delineate where there would be the boundary of sort of the partially molten region. Okay, I think because of the uncertainties in relationships like what you're talking about, and the interpretation of melt, I think it is somewhat uncertain about exactly where there you would draw your boundary for where the partial melt exists. Mark?
Yeah. So in this area, do you actually have also any constraints on just the total melt production? I mean, there's predictions about that as well. I mean, if it's hotter, there's heat and water are your
right
ingredients, okay, but do you see variations in crustal thickness or?
Yeah, there isn't much variation in crustal thickness, but there is big substantial variation in spreading rate. So, I mean, yeah, you can calculate, if you assume like you can estimate melt production from just the thickness of the crust, then as you go from the north to the south in the Lau Basin, so in the north you actually have several spreading ridges sort of in parallel, and it's just spreading apart very rapidly. Central Lao Spreading Center, I think, has something like, 8 centimeters per year or 80 millimeters per year, and then going southward you end up with something like 45, I think. So there is somewhat of a variation in the amount of melt being produced altogether, okay? But there isn't much variation in crustal thickness throughout this area. There is quite a big variation in the...
Well, that makes the lack of variation in crustal thickness makes me think your temperatures are far too high, right? I mean, if it's really as high as 1450, right, then the thickness of the crust should be 15, 20 kilometers.
Well, this is this whole argument with Charlie Langner that's been going on for a long time. Is how accurate are these kind of major element estimates of mantle potential temperatures, and because they fail to predict the thickness of crust in some areas, and I don't know. I think that's a bit beyond me as a seismologist, but the one area that I would say there is that the mantle is likely quite depleted in this whole region. So you probably have lower crustal generation because of the degree to which the mantle is depleted. Here, I should let you do that.
One of the easiest ways to explain the difference between resistivity and seismic is that you could have melt there the seismic is sensitive to, but if it's not interconnected at all, the resistivity won't see it.
Right.
So I guess another question would be, perhaps we don't fully understand wetting angles or what might be interstitial melt between melt bands that are whisking stuff away very quickly. And so, for example, in a place like Uturunco, there's a huge resistivity anomaly. It's at a very different depth than the seismic anomaly.
Mm-hmm.
They're apparently quite contradictory.
Yeah, I mean, but once again, I think that, the experimental evidence suggests that melt is interconnected to a very small melt fraction, like you said, unless there's something we don't understand. So.
Just to build on this question, maybe just the fact that you are sampling different directions, because this is one parameter also. You can have connectivity more in one direction than the other, and you are sampling more horizontally with the MT and more vertically with the seismic. May this also explain the difference?
I've asked the MT people that, and they claim that that wouldn't explain the difference in this case, but it would be nice if we had MT person here to discuss this with.
And I had another question that probably something I misunderstood, but when you are comparing QP and QS, you are saying that there is a process that is related to melt that makes a stronger bulk attenuation than shear attenuation?
Well, it's about the same bulk attenuation as shear attenuation, but that would be very unusual because everywhere else in the world we see no bulk attenuation. I mean, the mode data are quite clear that there's almost no bulk attenuation, in the whole Earth. So I guess my idea interpreting these results is that there's bulk attenuation, but it's only in very, very small regions where we have the melt. Okay, and in the rest of the Earth, there's no bulk attenuation, and that would be consistent with what the mode data show, which is that there's almost zero bulk attenuation in the whole Earth. The little bit of bulk attenuation that we have is in the very uppermost mantle, and then from this result, I would say that it's centered only in those regions where we have melt.
What are your VPVS ratios like then?
We don't, in the Lau Basin, we don't have our final VPVS models yet. But that certainly would affect VPVS. I mean, there's all sorts of arguments on the basis of the melt, how VPVS ratio would be affected. But then they would be changed by the fact that you would have bulk attenuation, because they usually assume that you don't have any bulk attenuation.
Garrett.
I was curious about the base of the melting zone, in particular your image for Q in contrast to what you're showing there. Can you show that image for your...
No, I'm going the wrong way, yeah. There.
Yeah, so that to the west, that the yellowish region extends, well below 100 kilometers. Does that imply there's melt below 100 kilometers? Or
Well,
what's the resolution?
Once again, as I was saying, in the response to Dan, putting a contour on one of these maps and saying within that contour we have melt, and outside of that contour we don't have melt, I don't think we're there yet. But definitely, I mean, well, a couple of things I would say here is, first of all, the resolution of the attenuation image is worse than the velocity image. But the other thing is the velocity image, because it's from surface waves, becomes less, loses resolution below 120 kilometers. So if we go to this would be the velocity image. So at 120 here, we're losing resolution on the surface waves. So directly comparing those two images is a bit difficult because of the different resolutions at different depths.
Nonetheless, there are big variations in Q, so unless they're temperature, they must be related to composition or melt. Your Q, right? So you can say, you can't tell me where the melt regime is, but there's something causing those big variations.
Oh yeah. And I would interpret this area at least as being due to melt. Probably this area, but whether this is due to melt or not, I wouldn't be able to speculate.
Yeah, you've shown on some of your pictures relationship between velocities and seismicity. Can you comment what kind of seismicity do we have in this potentially melt-driven area? Is it you know, like what is the mechanism and magnitudes and so on. Is there any, like this were in some of your very early images.
Well, let's see if I can go back to one that has the seismicity on it.
Yeah, here.
Oh, there we go. Yeah. Okay, so here we see the earthquakes, and the earthquakes are generally only in the slab. Not, you know, none of them are in this backarc region because it's too hot. And in Mariana, we do see a double seismic zone.
Yeah, no, but I mean, in the overriding plate region, you see many crosses, for example, in between your two volcanic centers.
Oh,
Yeah,
the depths of
one is
those.
in blue.
Yeah, the depths of those are not well constrained. So, and in fact, I think we failed to plot the final depths and just plot the initial depths on that map. So,
So this one is not very well studied, and then. Are these kind of low magnitude earthquakes, or you also have some large magnitude there in the overriding plate?
In the backarc.
Yeah.
Yeah. Those are generally magnitude 4 or so, so 3 to 4. I think there are occasionally magnitude 5 earthquakes there, but there are not magnitude 7s or something like that.
And did anyone suggest, let's say, something that looks like slow quakes or these transients or tremors for these magmatic regions?
No.
No.
No. I mean, we have, there was a student from Japan that worked in my lab for 6 months or a year, and he located an area of earthquakes along the backarc spreading center there, I guess where those crosses are mostly. And they're all shallower than about 12 kilometers. But we didn't detect any sort of tremor.
Okay.
That's not to say it doesn't exist there, but...
So while you have this picture up, so you haven't found in this region any volcanic earthquakes like occur beneath Northern Honshu?
Volcanic. Oh, you mean slow, like DLP? Deep
Well,
long period earthquake?
they have quite a different character.
Yeah,
If they're caused by melt movement itself. We see them in Iceland also.
right.
They're very easily recognized. They have much more emergent signal.
Right.
Still earthquakes, but they're quite distinguishable from the brittle failure ones.
Yeah. I mean, the ones I'm familiar with are these deep long period earthquakes that are about 25 kilometers deep or something like that, and are thought to be due to melt movement. And we didn't find any here. I found some in Antarctica, but haven't found them here.
More questions? Sean.
Yeah, I'm going to give a presentation on melt process at high temperature hydrogen with slightly different point of view. But yeah, I think in terms of observational constraints, the QP to QS ratio is a key. If indeed this ratio is as small as you showed, I think it's very difficult to explain without melt. So I think this is really important.
Yeah. That's good. I mean, I'm not familiar with any mechanism that you could explain it with really without melt, but it's good to hear your point of view. So.
I wondered about the amount of regularization that has gone into some of these images and whether you can, to what extent you can distinguish too high attenuation or too low velocity blobs that might represent the hydrous melting region and a decompression melting region. Is the fact that they're continuous in some of those later images simply an artifact of the amount of regularization or the resolution of the seismic imaging?
Yeah, that's a good question. We're working right now on trying to get P and S wave images from body waves, which would have potentially higher lateral resolution. I mean, it's not just the regularization that could be a problem here, but it's also the fact that we're using surface waves, which have, a longer wavelength. So, the wavelengths will kind of limit the resolution that you have, sort of independent even of the regularization. But yeah, the question would be whether you could get more structure out of this. And I don't think you really can with the data that we have with the long wavelengths. So basically that's at 50 or 40 kilometers deep. And so you're using sort of 60-second, you're using like 30-second surface waves to get that. So the wavelength of those waves is something like 120 kilometers. So that kind of limits the amount of resolution that you have. So in order to get better resolution, then we need to look at the body waves, which we haven't really quite finished yet. The Mariana image that I showed, let's see, where was it? This one was done with P waves, and so the wavelengths of those waves are smaller, and so we are here able to kind of nicely resolve the separation of the volcanic arc and the backarc spreading center. But so it'd be interesting to see what we see when we get that results for Tonga Lao. But I think there's quite substantial differences though between this system and the Tonga Lao system, because the inferred mantle temperatures are higher, and the backarc spreading center here is a slow spreading center, so probably has only episodic melt production rather than continuous melt supply. So,
do you use higher modes?
pardon?
Are you also using higher modes, or are these just the fundamental on the surface rate?
We're just using the fundamental. Yeah, we haven't used what we've done for the images, surface rate images, we've used noise correlation for the higher frequencies. So we use noise correlation between about 8 seconds and 20 seconds, and then we use the fundamental mode surface waves from earthquakes, Rayleigh waves from earthquakes from 20 to, I think it's 100 seconds. So.
But the noise also just the fundamental?
Yes, on this one we've just used the fundamental.
Charlie, that would be a higher modes on.
Yeah.
Correlation.
There's another study we're doing with OBSs where we do see the higher modes and we're using them, but I think on this one we just used the fundamental.
Okay, I think we should break for lunch now, but before we go, can we just thank Doug once again?